Hello students, welcome to the 33rd lecture on particle physics. And in the 32nd lecture, I was talking about star death, and we discussed about brown dwarf, black dwarf, white dwarf, as well as neutron stars. Let us start the discussion from the neutron stars. What I had told you that all those stars whose masses are more than 4 times the mass of the sun and less than 8 times mass of the sun, they will die as a neutron stars. Now what happens actually in these stars? First you have hydrogen fusion, then helium fusion, then mass is sufficient to have carbon fusion, oxygen fusion, up to silicon fusion. And then you have core of iron. And since you cannot have fission or fusion of iron nuclei, therefore there is no source of fresh fuel, while the gravitational collapse is still going on inside the core and the matters are falling, and that results in the increase in the temperature, and also these radiations they start the photodisintegration process, and the iron nuclei disintegrates into daughter nuclei and neutrons. Besides that, it consumes energy, and these neutrons they remain there. But besides neutrons, we have another important physics that gives rise to neutrinos happens, and this is what we were discussing in the last lecture. What we were talking about, that in massive red giants the temperatures and pressures are high enough to cause carbon to fuse into heavier elements like oxygen and silicon. At still higher temperatures, silicon may fuse to form even heavier elements like iron and nickel. And this is what you have, the onion shape. Outside of this core is like onion shape. You have had temperature is sufficient enough to still the fusion of hydrogen to helium, and then below that helium to carbon, and so on, and ultimately you have surrounding the inner core this silicon fusion taking place to have iron, and slowly and gradually the iron is building up inside the deep core of the star, and this process takes place at a very rapid rate. This is what we had discussed, that for massive stars hydrogen fusion will happen rapidly in comparison to stars which have got masses typically to that of solar mass. For example, the lifetime of sun in the main sequence is 10 power 9 billion years, while for such massive stars this lifetime is million years for the hydrogen to helium fusion. Then when they will become red giant and bigger than that, the helium to carbon will happen in 10 power 5 years. Carbon to oxygen burning will take place for 600 years, and ultimately silicon to iron burning will happen only in a day. And then core, since there is no fresh fuel, therefore core will collapse. Therefore the core mass is typically of 1.5 mass of the sun. Generally we say that it lies between 1.4 mass of the sun and 3 mass of the sun, which is known by the name Chandrasekhar limit. And at this point of time, the temperature is around 10 power 10 degree Kelvin, and the core's density is around billion gram per centimeter cube. Remember, the density of interstellar matter, the average density was 10 power minus 24 gram per centimeter cube. And then we had clouds, nebulae, which we called, and then we had globules. Still the density was 10 power minus 15, 10 power minus 14 gram per centimeter cube. Now we are talking about the place where the density is of the order of billion gram per centimeter cube. We have talked about the density of water and air in the last class, and therefore you can think of the weight of 1 centimeter cube in these type of stars. The stars start collapsing due to the photo disintegration of nuclei of iron group, and this results into alpha particle, neutrons, and it consumes energy. And then because the matter is coming very close to each other, then the electron gets captured by the proton, because still you have matter, and matter is nothing but electron and a proton, that those are present in the matter. Therefore, these electrons get captured. They also give rise to neutron and neutrino, and then electron is also captured by the other heavier nuclei present in the vicinity, and therefore you have another nuclei in the final state. Besides that, you have a neutrino in the final state. Now, initially, when the density is not so large, these neutrinos try to move out of that area, and because they are weakly interacting particle. But we will see that gradually when the density reaches to a value where or we can say that up to nuclear density, where these neutrinos won't be able to escape and they will also get trapped. Therefore, gradually a density inside the core reaches to 10 power 12 gram per centimeter cube, in which typical nuclei having mass 80 mass number to 100 mass number with 50 neutrons are produced. Then the neutrinos are, when the density becomes so large, neutrinos are unable to come out. The collapsing star finally reaches out to a density of 10 power 14 gram per centimeter cube, where the core becomes stiff and the neutron degeneracy comes into play. We talked about electron degeneracy in the case of white dwarf stars. In the case of neutron stars, we have the neutron degeneracy, as the neutrons are also fermions and they obey Pauli's exclusion principle. Therefore, once they have the lowest states they have filled, there is no space to further shrink, and therefore everything becomes very stiff. There is no scope of further shrinking inside the deep core. Then what happens? The infalling matter is still they are coming to this stiff core, and when they come, they bounce back from here, and when they bounce back, they produce shock waves, and these shock waves try to move out. Now, these shock waves, if they are strong enough, what they do, they explode the outer envelope of the star, and when they explode the outer envelope of the star, the neutrinos which were trapped because of the higher density, now they start moving out at a very rapid rate. It is estimated that almost in power 56 neutrinos they come out in a few seconds of time, and then the neutrons which were being made because of the photo disintegration, because of the electron capture by the proton, because of the electron capture by the nuclei, they also start moving out. Because with this flow of neutrinos, huge amount of neutrinos, they are flowing out. This is like air is flowing out, and when you have a huge wind, then these huge wind also takes away with it a small material particle like leaves and other things besides with it. Similarly here, this huge wind of neutrinos, along with it, neutrons also, they move out. But when the neutrons move out, they captured by the nuclei present in the vicinity, and depending upon the flux of neutrons those are coming out, that will depend upon the mass of the star, whether it is 8 times mass of the sun or whether that is 4 times mass of the sun. You will have the amount of neutrons. Therefore, this neutron capture by the nuclei gives rise to heavier nuclei in the star. That is why when we talk about this neutron capture, we talk about slow neutron capture and we talk about rapid neutron capture. Rapid neutron capture happens in those places where the neutron flux is very high, while slow neutron capture takes place at those places where the neutron flux is low. And this is what we are going to discuss today. Therefore, what I am telling you that in the supernova explosion, which is the explosion of the outer envelope and implosion of the core, these neutrinos, they try to move out. They are equal in numbers of all the fluxes that you talk about, but their energies are different. That is what we discussed yesterday, that nu E will have charge current as well as neutral current interaction, while nu mu and nu tau will have only neutral current interaction. Therefore, an energy carried by nu mu and nu tau will be higher than nu E. That means 10 power 60 million electron volts of energy that comes out, and energy carriers are nothing but neutrinos, and huge amount of neutrinos, they come out from the star, and what we are left with is a core, and that core is known as neutron stars. So therefore, the important point is that when shock waves are moving out, they are exploding the star outer envelope, and the neutrinos are then moving out with a very high speed, and there is a huge amount of neutrinos. Those are present in the vicinity of this core, and these neutrinos make supernovae explode. Neutrino push the shock waves and blow up the star. That is why supernova is known as the explosion of the outer envelope and the implosion of the core. The total number of neutrinos that reach Earth if a supernova explosion takes place in a galaxy like Large Magellanic Cloud, which is 50 kiloparsec away from here, will be around 2 into 10 power 10 neutrinos per centimeter cube, per centimeter square. And supernova 1987A were detected at Kamiokande and IMB detectors. And whenever a star explodes as a supernova, the most powerful explosion in the universe, 99% of its energy is carried by these neutrinos, and they constitute supernova neutrinos. Now we are going to talk about the formation of heavier elements inside the star's environment. Therefore, what if you remember what we had started with in the 31st lecture, that the elements that we see in the periodic table, except for the transuranic elements which we can create in the laboratory synthetically, all the elements except for hydrogen and major portion of helium, which were formed during Big Bang nucleosynthesis, all the elements, carbon, oxygen, calcium, silicon, iron, and others, heavier, uranium, thorium, bismuth, all were formed in the star's environment. Up to iron, the reason is nuclear fusion reaction giving rise to an iron core. But beyond that, it is the S process, P process, R process, nucleosynthesis, which is responsible for the formation of heavier elements. That this curve which I am showing here, on the x-axis we have the neutron number, on the y-axis we have the proton number, and this straight line is the n equal to z curve, because to a layman, if we talk about carbon nucleus, that is 6 protons, 6 neutrons. If we talk about oxygen nucleus, 8 protons and 8 neutrons. If we talk about calcium nucleus, 20 protons and 20 neutrons. Therefore, if we ask him or her to plot such type of curve, then it will be a straight line. But we know that it is not the straight line. because as we grow in the number of protons, we have more number of neutrons for the stability. As the protons, they will also interact via Coulomb interaction, while neutrons will have only strong interaction. Therefore, a strong interaction will give rise to an attractive force, while the protons which are interacting among themselves, they have both the strong interaction force as well as electromagnetic repulsion. But since we know that the range of electromagnetic interaction is infinite, while the range of strong interaction is of the order of Fermi. Therefore, when we are talking about a bigger nucleus, and say I am talking about a proton here and a proton here, and the distance is, since the radius of the nucleus is given by r naught a1 by third, r naught for low mass nuclei like carbon and oxygen is 1.1 Fermi. For medium sized nuclei like iron, it is 1.2 Fermi. And for heavier nuclei, it is around 1.3 Fermi. Now, A is, for example, if you talk about bismuth or uranium or thorium, is of the order of 240. Therefore, if A is 240 and R naught is 1.3, you can understand that this is a larger number, and that while the strong interaction range is only up to Fermi, therefore this proton of such type of nucleus is not going to interact with this proton via strong interaction. Or even if a neutron is present, then this proton is not going to interact with this neutron, which is well beyond a distance of Fermi. While electromagnetic interaction will be active and there will be Coulombic repulsion. Therefore, what nature does, nature fills more neutrons in such type of nucleus to have collective strong interaction effect, to nullify the Coulombic repulsion, to have a stable nucleus. That is why you have this stability curve which is tilted towards the neutron line. And then we are talking about the S process, slow process, rapid capture process. Similarly, we have P process for the formation of heavier elements of the periodic table. Now, before going ahead, let us talk about a very simple concept, though we have discussed it, that is beta decay. We know that a negatron decay is a neutron decaying into a proton plus electron plus antineutrino, while a beta plus decay, what that is known as positron decay, we have proton getting converted into neutron plus positron plus neutrino. Now, this means that a neutron is getting converted into proton. This guy is getting converted into another guy. Neutron is getting converted into proton, or proton is getting converted into neutron. We know that these are weak interaction processes. Therefore, the mediating quanta for this is W minus boson, while this is W plus boson. And neutron is getting converted into proton by emitting a W minus, and that W minus is giving rise to electron and antineutrino, or here W plus is giving rise to positron and a neutrino. Therefore, if you are away from the stability curve, if you have formed a nucleus away from the stability curve, then through this beta decay or releasing energy, that nucleus will try to come on the stability curve, which has been shown here by this broad band. We know that we cannot have nuclei, heavier nuclei, on this straight line. Initially, it is a straight line like for carbon, oxygen, calcium. But beyond that, we know that there should be more number of neutrons for a stable nucleus. Therefore, if you are forming a stable nucleus, then only it is going to exist. And if through neutron capture or through whatever process you talk about, you are forming an unstable nucleus, then it will like to come onto the stability curve. Now we are first talking about rapid process. As I have told you, this will happen where the neutron flux will be very high. In a rapid neutron capture process or R process, neutron captures are rapid. They happen more quickly than the beta decay can occur. So therefore, mind it, suppose inside the core of a star we have a ZX nuclei which was formed because of fusion reaction. Now a neutron is getting captured. You will have some other nucleus, but this nucleus is, for example, say unstable. Therefore, if it is unstable, then it will decay. But before it decays, since the flux of neutrinos are so high, it will capture another neutron. And again you see you have formed a say Z prime nucleus. And it is also unstable. But what is happening? There is so much of neutrons that before it decays, you have another neutron capture. And therefore, in the case of rapid neutron capture process, before a beta decay can happen, you have a heavier nucleus, and then a capture of neutron, another heavier nuclei, and so on. This will keep on happening unless you have a nucleus, something like I am writing like this, Z, just I am representing it by Z, which has a lifetime is smaller than the neutron capture time. That means, though the number of neutrons are more, though the capture is happening very rapidly, but still if you are forming very heavy nuclei, such that its lifetime is really small, then it decays before another neutron gets captured. And this is what we are going to talk about. The R process dominates in an environment which have a higher flux of free neutrons, almost like 10 power 24 free neutrons per centimeter cube. We are talking about a star's environment. Heavier elements and more neutron rich isotopes are produced. So this is what I am talking about, that you have a stable isotope. Neutron is added, you have another one. Another neutron is added, you have a second one, third one, and you, by doing this, you have reached up to a plus 20 nucleus. Now this one is different from this guy, as there are different number of neutrons. This may be stable or may not be stable. Now, if it is stable, a new isotope will be formed, or if it is not, then this will decay into some lighter nuclei, and that lighter nuclei may be a stable isotope, or other further it will decay to give you a stable isotope. Therefore, this neutron capture will happen rapidly, and you will have the formation of heavier elements, and then further heavier element, and then further higher heavier element, and so on. And this will keep on happening unless the lifetime of that nuclei becomes smaller than the neutron capture time, and then that nuclei will decay to a stable nuclei, or you will have then an element, a new element in the star's core. Now, what happens in the case of S process? S process is responsible for the nucleosynthesis of approximately half the atomic nuclei, heavier than iron. The S process is a series of reactions in nuclear astrophysics which occurs in stars having mass less than 10 mass of the sun. Mind it, I was talking about heavier star and less massive star, 4 times mass of the sun, 6 times mass of the sun, and 8 times mass of the sun, and 10 times mass of the sun. What I am talking about is that if they have low mass star, then you have slow neutron capture. If you have heavier star, you have rapid neutron capture, and that is what we were calling it as R process. Therefore, in that environment, when neutrons are coming out, those nuclei are getting captured, and you have those elements in the universe. And here in this case, what happens? A seed nucleus, any ZXA nucleus that you talked about, undergoes neutron capture to form an isotope with one higher atomic mass. Now you see, now here there are lesser number of neutrons. Therefore, this may happen that a neutron has got captured. If that nucleus is not a stable nucleus, before a neutron, another neutron gets captured, it decays. Because this time interval between the two neutron capture, because the neutron fluxes are small, that is large. This time interval of neutron capture is large, while the decay time for such nuclei is smaller than that neutron capture time. And that is why you don't have something like 20 neutron captures or 30 neutron captures. Rather, you have 1 or 2 neutron capture, or at the most 3 neutron captures, and then that nuclei is decaying into a stable nucleus, or that will form a stable nucleus. So it requires a neutron density of the order of 10 power 5 to 10 power 11 neutrons per centimeter square. Mind it, this is much smaller number in the case of when you compare it with the case of the stars, where you have the possibility of rapid neutron capture. That number was huge in comparison to this these type of stars environment. And if the newest isotope is stable, a series of increase in mass can occur. But if it is unstable, then again through a beta decay will occur, producing an element of the atomic number, say Z plus 1. Therefore, this is type of stability elements, those will be formed through the slow neutron capture. And this is what I am telling you, that the process is slow in the sense that there is a sufficient time for this radioactive decay to occur before another neutron is captured. This cycle stops the S process in the formation of 210 bismuth through the capture of neutron by 209 bismuth. Therefore, this is how you have the formation of heavier elements, and those are the elements which even we find in the seashore. And this is what I have shown here pictorially, that this is a stable isotope. You have one neutron capture. This can be stable, or this can decay into a stable isotope. This is how you are finding out the different higher elements in the universe. Thus, what we are saying is that the complete elements that we talk about, whether I talk about the water and oxygen, this hydrogen atom is from the Big Bang nucleosynthesis. The oxygen is from the star's core. The gold ring, the uranium on the seashore, or any element that you talk about was produced somewhere in the star's environment. And therefore, whether you talk about calcium in our teeth, iron in our blood, or carbon in our DNA, whatever you talk about, they are basically, their origin is somewhere the stars. And therefore, we are nothing but stardust. And let's stop here. And in the next lecture, I am going to talk about the other source of neutrino, and that is known by the name accelerator neutrinos. That is an artificial source of producing neutrinos, where we accelerate protons, and these protons strike the heavy target material like graphite. They produce pions and kaons, and these pions and kaons are then collimated using magnetic field, and then they produce while moving out to give rise to neutrinos. Stay tuned. See you in the next lecture. Thank you very much.